Hello everybody. Last time in a video we talked about how we can change the entropy of a system by rearranging the particles and putting them into sort of different physical arrangements, and that was positional entropy. And we went through a whole bunch of different ways that we could increase the entropy by rearranging the positions of the molecules. In this video what we're going to do is we're going to look at changes of entropy as it's associated with changes in the way the energy is arranged. Now, I think this concept is a little bit trickier to get in some ways than the concept of positional entropy, especially when we get into the idea of quantized energy. You might remember well, you don't remember, but about 100 years ago, physicists learned that energy wasn't a continuum. It came in discrete levels, right? A molecule could have this energy, or that energy, or that energy, but not any old amount of energy in between. And this idea of quantized energy is going to be important as we get through this conversation. So let's pick up here with talking about entropy changes and energy. So let's get our title out of the way here. And so we've already spent some time talking about this concept here. Positional entropy increases as the number of arrangements increase. What I want to get to now is this issue down here, that the entropy of a system can also increase if we take the energy within the system and we actually make it less so to call concentrated. Now, it's not concentrated in the way you make a solution concentrated, but if we have a certain amount of energy and we spread that energy out, then it's going to turn out that the entropy of that system is going to be going up. And so I have here a cartoon of a hot frying pan. Move it over here. Now, we all know if you have a hot frying pan and you turn the burner off, so let's pretend the burner isn't there anymore, and it's still hot, you know that in a matter of a few seconds or a few minutes, that hot frying pan clearly cools down. That is actually a result of the entropy of the universe being increased. Because what happens is the heat in that frying pan starts to get dissipated to the surrounding air molecules. So we take the energy that is concentrated in that metal frying pan and we dissipate it. We spread it out. We make it less concentrated by transferring that energy into the surrounding air molecules. So all the energy that used to be in that hot frying pan gets spread out into the surrounding air molecules. That would be an increase in the entropy. Now, we could also increase the entropy by spreading energy out in a slightly different way. Right? Cooling, I think, is a fairly easy way to see how energy is being spread out. But there's another way in which energy can be spread out, and this comes back to the issue of energy being quantized that I alluded to about 3 minutes ago. So let's go back to our good old glass of water that we have used before. So you know it's a glass of water because I'm putting in a blue squiggle line. Now, energy comes in different forms. If you think about a water molecule, and I'll draw one here, we've got a water molecule. The energy that any given water molecule has can be tied up in the molecule in different ways. For example, the energy it takes to move the molecule is called translational energy. And so a molecule can have a certain amount of translational energy. The molecule can rotate, so it could have rotational energy. And hopefully you know that the bonds of a molecule, that say OH bond, that can vibrate back and forth. And so it can have vibrational energy. So let's not get caught up into all the different kinds of energies a water molecule can have. Let's just talk energy in general. And it turns out that all of these specific kinds of energies, or energy in general, as I alluded to, isn't a continuum. Energy comes in levels, right? It's quantized. This is what guys like Bohr and Planck discovered about the physical world a little bit more than 100 years ago. So the energy of the water molecules in my system here, they could have that amount of energy, or that amount of energy, or that amount of energy, or that amount of energy. I'm not being really specific. I'm just showing you that the energy is quantized as we go up the ladder here. So let's make a simplifying case. Let's talk about 10 water molecules. So at some cool temperature, so we'll say that this is at a cooler temperature, I might have 4 water molecules that have a low amount of quantized energy, a few molecules that have a higher energy, and a few molecules that have higher energies still. So just like we know that energy is, a sample has a range of energies. Not every single molecule has exactly the same amount of energy. Some have low energies, some have high energies. Okay? So that would be at some cool temperature. Maybe it's room temperature water. Now let's take that same glass of water and we're going to heat it up. So I've got my water glass here, and now instead of it being cool, let's say that we've warmed it up and we've got some hot water. Now the molecules in that sample can be arranged energetically over a broader range of possibilities. So I have the lowest energy, then the next lowest, then the next, then the next, and then as the water molecules are getting hotter and hotter, an individual water molecule could access a higher quantized energy level. So now, maybe what I have is I have a few water molecules still at really low energy, a few higher, and then a few more higher, and then we have ones that are getting really up there in energy. So if you compare the arrangement over here on the left to the arrangement over here on the right, what you've noticed is that I've spread the energy out. I've made it less concentrated. So by adding energy to a system, you're making the entropy of that system go up in terms of the energy arrangements. Now all the molecules are still, in both containers, they're still inside the bulk of that liquid. So I actually haven't changed any positions. Nothing's happened to the positional entropy in these two examples, but I have increased the entropy in going from the cool molecule or the cool cup on the left to the hot cup on the right, because I've allowed the water molecules to be able to access a broader range of quantized energy levels. Now there is one important thing that I want to make sure I point out right now, and that is between these two examples, between this hot pan we talked about a few minutes ago and my glasses of water, I really haven't paid too much attention to where the entropy has gone up. You know in thermodynamics that we have a system, you know we have a surroundings, and you put the two ideas together and we have the whole universe. Now, in both of these scenarios, in my glasses here and in the hot pan there, the hot pan, entropy has gone up. But I've kind of played a little loose and fast in not really telling you exactly where the entropy has gone up, and that's something we're going to have to start to pay a little bit more closer attention to. So in future videos, when we talk about entropy changes, we're going to start talking about entropy changes if they're occurring in the surroundings, or if they're occurring in the system, or if they're occurring overall. Where is the entropy actually being affected? And we'll get to that in later videos. So the idea that we want to make sure we understand now are the two ideas. You can mess with entropy in two different ways. You can do it by messing with the physical arrangement of the molecules in space, positional entropy, or you can mess with entropy by rearranging how the energy of a system or the surroundings or the universe is ultimately affected. Is it more concentrated or is it less concentrated? All right, we'll get to the issues of system, surroundings, and universe a little bit later in a future video. All right, that's it for now.